Julian Panetta from the Ecole Polytechnique Fédérale de Lausanne, who's going to talk on computational design of robust elastic metamaterials and deployable structures.
Thanks. And first, I'd like to thank the organizers for inviting me to speak here. I'm really excited to get to share my work with you. I'll be talking today about two rather distinct projects. The first topic of designing robust elastic metamaterials is probably most relevant to the people in this workshop. But because this work is a couple years old, I also wanted to talk about some of my more recent work on designing deployable structures. So I work in the field of computer graphics, and the computer graphics community's interest in designing metamaterials is largely motivated by recent advancements in additive fabrication technologies that have brought high-resolution 3D printing technologies into the reach of average consumers. And 3D printers are great in that you can fabricate very high-resolution, complex, intricate structures just as easily and as cheaply as simple solid objects, sometimes even more cheaply because of the reduction in material use. But our work tackles one of the key drawbacks of 3D printing, which is that it provides a limited range of elastic printing materials. For instance, on most mainstream printers, it's not possible to print two solid objects that deform by different amounts under the same load, because you're usually restricted to a single printing material at a time. And it's even more hopeless to spatially vary the material smoothly across a print. The application we envision is to be able to design objects that deform in interesting ways under prescribed loads. For instance, by varying the elastic properties in these structures, we can make them twist or buckle in certain patterns when simply compressed axially. Our approach is to alter the 3D print's geometry at a microscopic scale to create a wide range of different elastic behaviors. And I'd like to emphasize a key way that my work differs from a lot of the other microstructure works presented at this workshop, which is that we're not interested in finding the stiffest or lightest weight structure, but instead we're interested in covering some wide gamut of different material behaviors. It's currently impossible with today's computers to directly optimize the full design at the printing resolution. So even a consumer level printer like the B9 Creator shown here already has over 8 billion voxels resolution to work with. So if we wanted to design at the resolution we can print with, we'd be solving optimization problems with billions of variables. So instead, we want to decompose the design problem into two scales. First, we want to build some library of microstructure building blocks that get us material properties that we want. And then we want to use these microstructures to fabricate spatially varying material fields that we can design on a coarse-scale mesh. So the fabrication pipeline that we have developed consists of a pre-computation stage where we construct a whole database of periodic microstructures for a wide range of isotropic elasticity tensors. And then to fabricate a particular multi-material design, we simply look up the microstructure corresponding to each material property and place it within the corresponding cell of our coarse mesh, and then stitch the microstructures together to achieve a single material fabricatable design. In the end, we'll be able to fabricate objects that deform in particular user-specified ways under prescribed loads. But one of the challenges that we face and need to address is that these intricate microstructured objects tend to be very fragile. So we want to design microstructures that are less likely to fail in general use. Fortunately, for any desired material property, there's a surprisingly large space of geometries that will achieve that Hooke's law. So we can search the space to find the most robust structure. To achieve this goal of robust metamaterial design, we'll need a failure criterion capable of predicting failure under arbitrary loads applied to the microstructure. We'll need to define a sufficiently diverse family of shapes to run our optimization over. And we'll need to be able to compute gradients accurately of this failure criterion to run some shape optimization. So we apply the standard tool of periodic homogenization for linear elasticity to determine the effective material properties produced by a given microstructure. But we build on this theory a practical load-agnostic measure of how likely the microstructure is to break. Microstructured objects can break even when very small loads are applied to the structure they're fabricated in. And we can understand why by zooming in on the deformed microstructure and noting stress concentrations that greatly exceed the average stress value in the cell. So this means even if you apply a fairly mild stress on average to a microstructure, it could experience very high localized stresses in fracture. Computing both the effective material properties of a periodic microstructure and the pointwise stresses that it will experience can be done quite efficiently with periodic homogenization. We begin by stretching an infinite periodic tiling of our microstructure by some average strain tensor epsilon bar. We can then compute the tiling's actual deformation under this applied strain by minimizing the elastic energy stored in the tiling over all deformations whose periodic strain averages to the applied epsilon bar. And this is just solving a standard linear elasticity periodic cell problem that you're familiar with. Then we compute the stress at each point in the microstructure, and we can average the stresses as well to get the average stress in the microstructure. So because we're using linear elasticity, each step in this pipeline is linear, meaning there's a linear map from the applied macroscopic strain to the pointwise stresses appearing in the microstructure. And there's also a linear map from the macroscopic strain to the average stress appearing in the microstructure, which is just given by the homogenized elasticity tensor. So we can compute these two tensors that I've defined. So I defined a tensor M to give a map from the macroscopic strain to the microscopic pointwise stress. And we have the homogenized elasticity tensor CH. Both of them can be computed by evaluating these maps on a basis for strain tensors. So this essentially is just applying these three carefully chosen strains to our unit cell and computing these pointwise and average stress values in the cell. So this is done by solving the standard periodic cell problem shown here, and then computing averages of the stress and pointwise stress and storing them in slices of these tensors CH and M. And then once we have these two tensors, we can compute the average and pointwise stresses corresponding to a given macroscopic strain just by simple tensor multiplication. So it becomes very efficient. So we're now able to predict the pointwise stresses very efficiently. And we want to solve this problem. We want to find a microstructure geometry that achieves some user-specified material properties while also avoiding fractures as predicted by this microscopic stress. But of course, the challenge here is the stress fields that we see in the microstructure depend on the load that's applied. And this is a problem because we don't know the loading scenario, because our goal here is to create a database of general purpose materials that can be used in many different macroscopic designs under many different loading scenarios. So to guarantee microstructure robustness in arbitrary use cases, we must consider the worst case load that could be applied to the microstructure. So we already considered the worst case stress analysis problem for macro scale objects in our 2013 paper, Worst Case Structural Analysis, where we looked at the best way of distributing some fixed force budget over the surface of our object to maximize stress at given points in the object. But in the end, to solve this problem efficiently, we could only do it with an approximate heuristic, and it still was fairly expensive. But we discovered that the worst case stress analysis problem is greatly simplified in the periodic homogenization setting. So here, the applied load takes the form of an average stress tensor, sigma bar. Then there's going to be a linear map from this load to the macroscopic stress experienced at each point in the microstructure. And we construct this map explicitly by using the homogenized elasticity tensor to find the strain corresponding to sigma bar, to find the macroscopic strain corresponding to sigma bar, and then using our tensor field M that we defined to compute the pointwise stress. So we now have just another linear map from macroscopic stress to microscopic stress that we can call the tensor field F. So now we can formulate the worst case stress analysis problem at a point X by choosing some failure criterion and maximizing over the possible macroscopic stresses applied to the cell. So for instance, we could look at maximum principal stress as our failure criterion for brittle materials, or von Mises stress for ductile materials. And in both cases, it turns out that this maximization can be written as a special type of eigenvalue problem for fourth order tensors. So for the maximum principal stress, it turns out to be this fourth order tensor eigenvalue problem shown here. And for von Mises stress, it's even simpler. It's just a standard eigenvalue problem after we've applied some flattening convention to our rank 4 tensors. So this problem is so efficient to solve now that we can do it at every simulation element in our mesh in essentially negligible time after we've run the homogenization. So here I've shown an example where I've computed the worst case stress at every element in the structure. And I want to emphasize that at each point, the stress value that I show is for a different load that was chosen to be the worst load for that point. And for the peak value circled here, we found this worst case load shown on the right that's most efficient at breaking the structure there. And surprisingly, it doesn't matter much which failure criterion we use, because in the regions of highest worst case stress, we actually have a single eigenvalue that's non-zero. And so that means both the von Mises and principal stress measures are the same. And this is especially helpful also when it will come time to optimize these worst case stresses, because this large gap from the largest eigenvalue to the rest means that our eigenvalues will be differentiable. So with our stress analysis framework in place, we can now begin designing structures that experience minimal worst case stresses. Since structural failure is determined by the weakest point, we want to look at the maximum stress occurring anywhere in the structure. But of course, this objective is non-smooth and very difficult to optimize. So instead, we look at an LP norm of the worst case stress and choose a high enough p-value that we're really penalizing the maximum. So in our experiments, we used p equals 12. Finally, we formulate the design problem of a minimization of the single worst case stress measure over all principal microstructure geometries that achieve our desired Hooke's law. So to solve this optimization problem, we must first define a space of geometries to search over. And our goals in designing this space is to pick structures that will cover a broad range of material properties that will enable us to reduce stress significantly, that will still allow ourselves to connect structures designed for different materials together in the same print, and that will be able to satisfy our fabrication constraints for our 3D printers. We use an extended version of a parametric design space we introduced in our elastic textures paper for this process. And this consists of defining a topology by specifying some graph, and then specifying thickness and position parameters that control the location of the nodes in this graph and the thickness to which we inflate each edge to produce our geometry. So in this way, we have a truss-like structure shown on the right that's parameterized by position and thickness variables once a topology is chosen. The key advantage of using a parametric design space like this is it becomes very simple to enforce our fabrication constraints. This is as opposed to level set or SIMP-based topology optimization, where it requires more complicated techniques. So for instance, we have a constraint that we can't allow voids to be enclosed by material in our design, and this is satisfied automatically by picking frame structures. We have constraints on the minimal thickness that we can print, and this is just going to be a bound on our thickness variables in the optimization. And then self-supporting constraints can be expressed with linear inequality constraints, as I'll show later. It also becomes much simpler to ensure that microstructures for different material properties can be pieced together into a single printable design. First, we must ensure that we have compatible topologies for the different cells. So what this means is we need the same nodes on the interfaces of the cells so that we know how to stitch these structures together. And so we enforce this constraint by partitioning our topologies into families that have these matching interfaces. Second, we can add regularization terms to our design problem. Ooh, this is quite difficult to see. That will promote a smooth map from material properties to microstructures. And this is needed to work around the issue that there are many different structures that map to the same material properties. And with this regularization, we're able to create, for instance, isotropic structures that smoothly interpolate over the full range of possible Poisson's ratio values. So here we show a structure that interpolates from nearly -1, -0.98, up to 0.95. And because the parameters change so slowly, it's easy to stitch together structures for nearby material properties in the final design. And I can show a little bit more contrast here. An example here, I'm plotting Young's modulus and Poisson's ratio. And these are structures I've designed for the different material properties. And we see that the structure varies quite smoothly as we look at different material properties. So the full set of topologies we consider come from some combinatorial enumeration of all possible ways of connecting bars within our unit cell under some simplicity and symmetry constraints to reduce the search. And with these constraints, we have 1,205 different topologies to consider, and they're partitioned into 138 different families that can, within each family, we know we can piece together the topologies. Now let's look at how we define our parametric space of shapes for a given topology. For good stress performance, we're going to need to be able to produce very smooth geometry, and for this we use implicit surface modeling. We define our geometry as the zero level set of some analytical sign distance function built by smoothly blending together sign distances to primitives for the bars in our structure. I'll illustrate this process in a 2D example. So we assign each graph vertex a radius, which will define a sphere, and then we form the geometry of each inflated edge as the convex hull of the two endpoint spheres. Then we compute the geometry of each joint by smoothly blending together the incident edge primitives, and then we blend everything together to get our final structure. So here we have a nice smoothly rounded corner in our structure. Unioning shapes in the implicit surface modeling framework is quite simple. You'll just take the minimum of two sign distance functions to compute an exact minimum. But of course, this is going to lead to creases in the resulting geometry, which in linear elasticity would concentrate infinite stress at the corner here. So we need to be able to round off these corners, and we do that by using a smooth approximation to the minimum shown here. So this will deposit extra material where the two original isolines coincide and round off the corner. So we can now look a bit more carefully at the self-supporting constraint, because it will actually force us to change a bit how we formulate our parametric design. So here we're requiring each point in the structure to be above some, be connected to some other point that was printed at a previous layer. And this can be enforced easily on the edge primitive geometry just by requiring the bottom point of one of these spheres to be above the bottom point of at least one of its neighbors. And in the end, this boils down to just simple linear inequality constraints on the positions and radii of these spheres. But even with these constraints ensuring that the edge primitives are printable, we can still get unprintable geometry due to what's called a bulging phenomenon in implicit surface modeling. So this is a notorious problem where you can't easily control where this extra material is added to round off corners. So here the blending operator can add material hanging below the edge primitives, which were designed to be printable. And then this added material is not supported by the rest of the structure. And it turns out that none of the existing works tackling this bulging problem do it in a way that can conserve the self-supporting property of our edge network. So we introduced a new blending algorithm that preserves the self-supporting property. And we begin by noticing that material added outside the convex hull of the edge primitives risk being unsupported. And because the edge primitives are smooth and convex, all union geometry touching this convex hull is going to be smooth already and doesn't need additional material to smooth it. However, we do want smoothing inside the convex hull, where the material will be supported by the edge geometry. So essentially, we just modify our blending operator to only apply the smoothing to only deposit additional material inside the convex hull of the edge primitives. So here we see a 3D example before and after enabling this restricted convex hull blend. The unrestricted blending creates these bulges that hang below this dashed line, which indicates what's supported by the edge network geometry. And after applying our convex hull restricted blend, we no longer have these unsupported features. So with our parametric microstructure model in place, we're finally ready to solve this design problem. This is a constrained nonlinear optimization problem, and to solve it efficiently, we'll need to compute gradients of both the worst case stress objective and also the constraints on the homogenized tensor. We compute gradients in two steps using the chain rule. First, we determine how changing our design parameters perturb points on the boundary of our structure, and then we figure out how changes, how shape velocity on the boundary of our structure changes the objective and constraints of our optimization problem. So the first step is easy. We can determine how the shape evolves as we change some parameter pi of our structure just by differentiating both sides of the level set equation. And because our level set equation is implemented in our code as an analytical function of both the position and the parameters, we can compute all the derivatives shown here with automatic differentiation, which requires no additional derivations on our part. So this will give us a formula for the shape velocity, which I'm calling v here, or at least the normal component of the shape velocity, which is what we need. Now we need to compute how the worst case stress objective changes as we perturb the boundary in this way. The obvious approach is to use the standard boundary integral formula for the shape derivative shown here. And this formula is nice because it involves integrating surface quantities we already know, like the boundary velocity, or that we can compute easily by solving adjoint equations. Specifically for our problem, evaluating the shape derivative involves computing one adjoint cell problem for each of the original cell problem PDEs that we solved, and then computing the boundary integral shown here. Unfortunately, for our nearly non-smooth LP optimization objective, this formula turns out to be extremely inaccurate at getting us our parametric gradients. We trace this inaccuracy to an integration by parts step in the derivation of the boundary integral formula that doesn't actually hold in the discrete setting. So here, what I'm plotting is the derivative with respect to one of the parameters in my structure at different values of that parameter. I'm plotting a centered finite difference estimate of the derivative as my ground truth, and the gradient I get from this boundary integral formula is way off by several orders of magnitude. So we got much more accurate gradients by using an exact discrete derivative, meaning the derivative of our objective function with respect to each mesh vertex. And this can still be derived by discretizing a continuous shape derivative formula, but you need to use the slightly more involved volume integral-based formula shown here. And the same adjoint state as we solved before enters into this formula, so you don't have to change your adjoint problems. The one tricky thing is that this formula now depends on the velocities of the interior nodes of our mesh. But this isn't so surprising because, in fact, the finite element stress fields will be sensitive to perturbations of the interior mesh nodes. So to obtain accurate shape derivatives, we also need to somehow extend the shape velocity that we only know on the boundary of our structure into the interior. And we can do this with a smooth harmonic interpolation. So we solve a Laplace equation with Dirichlet boundary conditions on this geometry. And we found that this gives very accurate shape derivatives, essentially because this interpolated velocity field would keep elements well-shaped if we flow the mesh in this direction. So nothing is degenerating in our mesh. The results from this volume integral formula agree very well with the centered finite difference approximations as shown at the top. And the green line here is showing the volume integral formula, but not extending the velocity into the interior. So just setting the velocity equal to 0 at every internal mesh node. That still does better than the boundary integral formula, but not as well as it could. So finally, with our accurate gradients, we're ready to solve our optimization problem. We use sequential quadratic programming with a BFGS Hessian approximation. And at each iterate, we first mesh the geometry corresponding to the design parameters with tetrahedra. We run our periodic homogenization and worst-case stress analysis, so we solve our cell problems and compute these eigenvalues at each point on the mesh. We compute our shape velocities by differentiating our level set function. We construct our shape derivatives as shown before. And then we plug the shape velocities into the shape derivatives to get our derivatives with respect to our design parameters. So now I can show you some results generated with our minimal stress microstructure design tool. So first I can show the range of isotropic material properties we're able to cover with this parametric design space. So the Young's moduli here are plotted on the log scale, and they range from the full stiffness of our printing material down to 50,000 times less stiff. So we're able to get extremely flexible structures with this approach. And our Poisson's ratio for these 3D structures range from minus 0.75 up to 0.5. So each colored region here corresponds to one of the 6 topologies shown in the margins, but all of these 6 topologies belong to the same family, which means any material property I show in this plot can be used with any other in the same design. Next, we demonstrate our stress reduction with the following experiment. So first, we design an initial structure without penalizing the worst case stress. So finding some design in our smooth parametric design space that fits the elasticity tensor, but without caring about stress. And then starting from that design, we add our worst case stress objective to the problem and measure how much we are able to reduce that worst case stress. So this plot shows a reduction of roughly 5 times as typical, but we get less reduction near the boundary of the achievable space because there are fewer structures there that are able to achieve these extremal properties. And here are some specific designs from our database. So here's a structure producing a Young's modulus over 100 times softer than the printing material. And before we run our optimization, we see these high stress regions in red and also appearing in the histograms on the right. But after we penalize worst case stress, we're able to smooth away these stress concentrations while keeping the elastic properties identical. Here's an even softer structure, again showing high stress concentrations in the naive design that are smoothed away with our optimization. And here's a negative Poisson's ratio example, also showing good reduction. We ran lab tests to validate our optimized structure's robustness. And while it's difficult to apply the worst case load in the lab, we found that the improvement to our structures was still visible even in simple compression tests. We found the optimized structures survived much larger compressions than their unoptimized counterparts after testing a variety of different structures with different effective material properties. So to summarize this work's contribution, we developed a novel, efficient, and exact worst-case stress analysis for periodic microstructures. We introduced a new implicit surface blending operator to design smooth, printable parametric microstructures. We developed an accurate approach for computing gradients for parametric shape optimization problems of high P, LP norm stress objectives. And combining these components, we designed a microstructure database that achieves significant stress reduction. And the work I presented is discussed in more detail in this SIGGRAPH paper from 2017, if you want more detail. So the other project I'd like to present to you today is about a new class of deployable beam structures that we're calling Ecole. To give some broader context for this work, our group has been interested in some time in encoding a doubly curved surface into a flat sheet of material. For instance, our group had a SIGGRAPH paper last year on how to design this specific pattern of cuts to be placed into a flat sheet of material so that the material can uniformly expand up to some stretching limit. And once the material is fully expanded everywhere, it's forced to reproduce a particular doubly curved surface. This enables rapid deployment of by several simple expansion techniques like inflation, shown here. Eggshells are a related concept where you can encode your target 3D shape into a flat layout of elastic beams that are then easily assembled in plane and deployed by simply expanding the structure. Our eggshells are a variant of elastic grid shells, an architectural technique that dates back to the 1960s. Elastic grid shells are curved shell-like structures formed by continuous bent beams of material. The curved nature of the structure yields nice aesthetics and good structural robustness. And the sparse grid patterns employed lead to much more efficient material use than a solid shell structure. Unfortunately, surprisingly few of these grid shells have been constructed, partly due to deficiencies in the design tools for them and also challenges in deploying them. So for instance, this grid shell was built by, so you take a regular grid of beams and you connect them with joints in the plane, but then you have to somehow lift this entire grid, say with a crane, and then manually deform the boundary points into their target positions. So the shape arises entirely due to how the boundary is deformed into the supports. And this is a somewhat delicate process, and also beams often fracture when lifted like this. Our Eggshell solution to this deployment challenge takes inspiration from kinetic linkage structures like the Hoberman sphere, which have a single degree of freedom parametrizing their deployment from some compact configuration to their expanded configuration. And in fact, traditional grid shells are already behaving like a particularly uninteresting type of linkage structure shown on the left, which will just uniformly expand in plane. So this is a zero energy mode I'm showing here on the left. The basic idea of eggshells is to take this regular linkage structure and vary the spacing between the joints. This varied spacing leads to an incompatibility in the expansion deformation, which forces the structure to buckle into 3D, while still qualitatively preserving the single degree of freedom behavior. And by that I mean there's still a single easily actuated deformation path from the flat configuration to the deployed configuration. While we don't yet have a formal classification for the types of shapes we can produce with this approach, we've been able to create a surprisingly diverse collection of designs. At the core of our computational design framework is an efficient, near real-time simulation for this class of structure. We model eggshells as an assembly of discrete elastic rods. The discrete elastic rods model originated in the graphics community, but it's since been adopted by many mechanical engineering groups due to its high efficiency and high accuracy. The discrete elastic rods model allows us to simulate each beam of our structure as a one-dimensional polygonal curve. By defining a frame on each edge of this curve, we're able to efficiently express the orientation of the material cross-section as a single angle. So I'm calling this angle theta, which is expressed with respect to the material frame M, or reference frame for the curve M. So this in turn allows us to model the energy stored in the rod's twisting as well as its bending and stretching. And this is a geometrically nonlinear model, which has proven remarkably accurate in predicting real-world deformations of these rods. So we simulate the discrete elastic rods by minimizing a sum of three energies: a stretching energy, a bending energy, and a twisting energy. The stretching energy is based on a simple 1D strain measure. Bending is based on a discrete differential geometry discretization of the curvature binormal vector of the curve. And the twisting energy is based on a measure of how much the material frame rotates when going from one edge to the next. Our implementation can model rods with arbitrary cross-section geometries and arbitrary isotropic material properties. The user simply specifies the cross-section geometry and a Young's modulus and shear's modulus for the material. Then we can compute the stretching, bending, and twisting stiffnesses that appear in our elastic energy formulas directly from this geometry. So the stretching stiffness is just the cross-sectional area of our cross-section multiplied by the Young's modulus. The bending stiffness is just the moment of inertia tensor of the cross-section multiplied by Young's modulus. The twisting stiffness is slightly more complicated, so to find it, we run a simulation where we apply a unit twist to our rod, and we compute how the cross-sections warp out of plane to remain in equilibrium. And we can solve for this out-of-plane deformation I call psi here with a simple Laplace equation with Neumann boundary conditions. Now that we can simulate the behavior of a single rod, we can look at how we model our eggshells. So the input to our simulation tool is a graph where we have positions for each vertex. Each edge in this graph becomes a small piece of elastic rod, and the vertices become either scissor joints or free ends of the structure. In our simulation model, the joints don't store any elastic energy. So the elastic energy in the structure is just the sum over all of the rods in the structure of each rod's individual elastic energies. The design parameters of our structures are the rest lengths of the rod segments between each joint in the structure. And these appear directly in the expressions for our elastic energies. To avoid an expensive constrained optimization to simulate the equilibria of these structures, we eliminate the joint constraints by using a reduced set of variables. So the joints are constraining rods to pass through a common point and to have compatible orientations. So specifically, the rods are allowed to rotate relative to each other, but one rod is not able to rotate axially due to how they're bolted together. So we can define variables on each joint that parameterize this admissible set of deformations, as shown here. So basically we have an opening angle variable alpha, we have variables controlling the orientation of each joint, and variables specifying the lengths of the incident edges. And then, so these joint variables completely determine the state of the ends of our discrete elastic rods spanning between joints. And we only have variables from each elastic rod from the edges and vertices in the interior of the rod. So as mentioned before, eggshells behave essentially like a single degree of freedom structure. So there are several different ways we could actuate them. And the one that we chose is to specify an average opening angle over all the angles in the structures as a constraint, and then minimize the elastic energy everywhere else. Physically, this corresponds to applying the same torque to every joint in the structure and scaling the torque until the structure has deployed to the specified average opening angle. So I can quickly show you a demo of this running live. So here's a simple design that deploys into a hyperboid shape. Sorry. That's very strange. Okay, well, let's try this one. This one's more interesting anyway. So we see that even though this is a highly non-convex optimization problem to solve for the equilibrium, it still runs mostly in real time due to our efficient solvers. So specifically, the challenges we had to address is that the extreme stiffness of the rods to stretching means that the Hessian's eigenvalues, we have very large and very small eigenvalues of the elastic energy Hessian. And falling back to explicit force integration will make basically no progress. So we need a very efficient way of computing the Hessian and also modifying it to be positive definite during the optimization. And this is especially challenging because unstable equilibria are everywhere in the energy landscape for these eggshells. And in particular, we start in a flat configuration that doesn't have a preferred direction to, so it's reflectionally symmetric, so it doesn't know whether to pop up or down. So we need our numerical methods to break that symmetry robustly. So you might wonder why I said computing Hessians is, we need efficient Hessian computation because it should be easy. And in fact, we have formulas from these papers and even books on the Hessians, but it turns out that all of these formulas are wrong. So in our paper, we find these extra terms to the Hessian that are related to how the reference frame is parallel transported to the next curves configuration. But I need to skip over that. Another big challenge, as I mentioned, is coping with the indefiniteness of the elastic energy Hessian. So at the moment our structure wants to pop out of plane, our elastic energy, the Hessian of our elastic energy is indefinite. And to apply a Newton type method, we need to modify it. So we have some efficient strategies we've developed for dealing with this. And also for computing efficiently directions of negative curvature to escape saddle points. There's also a challenge in how to robustly optimize over rotations, and I've developed a standalone C++ library for optimizing over rotations using the tangent space to SO3 as the variables. And so this library will robustly compute gradients, Hessians, and allow you to compute higher order derivatives with automatic differentiation. So I quickly want to talk about the design optimization that we run for these structures. So manually designed layouts are going to have high stresses when we pull them open. And it's extremely challenging to manually adjust the spacing between the joints to ensure that you have nicely unwiggly rods that still approximate the target surface that you have in mind. So to ease the process of designing low-stress structures, we provide an optimization-based tool. So here, the objective of the optimization is to minimize the elastic energy stored in two states of the structure. We want a low energy flat state for easy fabrication. We also want a low energy deployed state, so the structure is robust once deployed. And we want our structure to stay close to some target surface. So this objective is expressed in terms of the equilibrium of our structure, which is found by running a nonlinear optimization to compute the equilibrium in the inner loop of this outer optimization. Then we have constraints on our structure that it's actually flat in its assembly configuration, and that it doesn't fold over itself, so that the angles remain positive in the plane when we start optimizing the structure. And again, the design parameters are the rest lengths between the joints in our structure. So we solved the design problem by computing gradients with the adjoint method, which is quite standard. And then one challenge is what optimization algorithm we use for solving this problem. So in particular, if we use a backtracking line search-based method for solving the problem, it will try to take large steps, which then will move us far away from the region where our inner equilibrium solver will converge rapidly. So one strategy that we found for fixing this is to use a trust region method and to limit the number of iterations our inner equilibrium solver is allowed to take. And so this means that the trust region solver will eventually find a reasonable radius and parameter space that it's able to move in while still efficiently solving the nonlinear equilibrium problems in the inner loop. So also we found that we need second order derivative information to efficiently solve this problem. So if we use something like BFGS to minimize the energy, we find it takes many iterations to converge. And remember, at each iteration, we have to solve a nonlinear equilibrium problem. So instead, we're using a Newton CG algorithm, which doesn't require the full Hessian of our objective function and constraints, but instead just Hessian vector products, so just directional derivatives of our design gradients. And so this can be done efficiently. The formulas just get a little bit more complicated. Essentially, what happens is we differentiate both sides of our state and adjoint equations with respect to the design parameters to figure out how perturbations in the, to figure out how our parameter step, delta p, that we're computing our Hessian, our directional derivative along, how that parameter step changes the equilibrium and changes the adjoint state. Then we can plug these changes in equilibrium and adjoint state into this formula here to compute the Hessian vector product. So the only challenge here is now we have third derivatives appearing of our elastic energy, which would have very, very scary expressions if we were to derive them by hand. But thankfully, because we have efficient hand-coded Hessian expressions for elastic energy, we can use automatic differentiation to compute the third derivatives. And one other trick that we needed to do to speed up the optimization was to use a quadratic Taylor expansion of our equilibrium position along the search direction of our outer design optimization to predict the equilibrium at the stepped parameter positions. And this is to make the inner equilibrium solve converge more rapidly. So we have a better initial guess for the equilibrium at the new design parameters. So this design optimization is able to significantly reduce the stresses in the design while still preserving the general shape of the structure. So here we're able to get a reduction of over 5 times in the deployed energy configuration and 7 times in the assembly configuration. And in interest of time, I will just run the video here instead of running it live. So this shows you the bars straightening out in the optimization, all while keeping the structure flat in its closed configuration and still approximating the target surface. So at each step of this optimization that I'm showing, I'm having to resolve this nonlinear equilibrium problem. So the last problem that we solved about eggshells is how to efficiently deploy them. So the simulation formulation I showed you was assuming that we apply torques to every single joint in the structure, which is not practical in real applications. So instead, we want to find some sparse subset of the joints to actuate while still producing the target shape. So thankfully, since our structure has nearly a single degree of freedom, it's not so sensitive to where we apply the torques or how many joints we apply the torques to. But still, choosing these torques intelligently gives us much better results. So we can formulate this as within a sparsity-inducing regularization term. So we reformulate our optimization to find the equilibrium in terms of a vector of torques applied to each joint. And then we can minimize the distance from our equilibrium to the target surface with some sparsity-inducing regularization term on the torques. So this is going to try to drive the torques on most of the joints to 0. So I can just quickly show you the results here. So with an L1 sparsity-inducing regularization term, we get many fewer actuators, but we can actually do much better with an L1/2 term. So that will give us, for a given admissible distance from the surface, many fewer actuators than a standard L1 sparsity-inducing regularization would. So maybe I can show you some physical prototypes that we built now. So here we weren't able to get torque actuators. We instead pulled the structure open with ropes, but where we attached the ropes was still informed by the optimized actuation locations. Here's a structure made of wood. And all of these were actually assembled manually by one person. So it's quite easy to put these together. And this one is made of fiberglass beams. And we can quickly compare how the deployed configuration and flat configuration are how well they're predicted by our simulation, as shown on the top. We found the match to be quite close. So unfortunately, when deploying the wood structure, we had one of the beams break, but when we inspected it more carefully, we saw it was due to a material defect in the beams. So we're not going to blame our method on that. So I'll quickly conclude with a discussion of some challenges that we met during this project that we don't have a perfect solution for yet. So we're always looking for better schemes for modifying our Hessian that will allow us to escape these unstable equilibria more efficiently. One thing that would help a lot is if we have an efficient way of estimating the most negative eigenvalue of our sparse Hessian matrix. In the graphics community, there's techniques of, instead of applying a modification to the full elastic energy Hessian, doing it on a per element basis. So in this case, per vertex of our rod, we could apply some modification to that per element Hessian to make it positive definite. Another thing we'd like to have is a smarter trust region algorithm for figuring out how far we can step in our outer optimization while still having a rapidly converging equilibrium solve inside. And finally, we still haven't yet formulated a full inverse design tool where a user can give us an arbitrary surface and we can come up with one of these X shells. So all of the designs I showed you were made by some combination of manual exploration and then running this optimization as a post-process. So with that, I'd like to thank you and take questions if we have some time.
Questions?
Can you recall what are the design variables in your deployable structures? This is length of...
Yeah, so currently it's just the rest length of the rod between two adjacent joints. But in the future, we'd like to look at optimizing the cross-section. And
size of fixes and it's better to use the length rather than the position of the nodes?
yes, because it's unclear what the position of the nodes is, because we have to solve for a flat equilibrium and a deployed equilibrium. So I think the lengths are the only thing it really makes sense to specify. Mm-hmm.
With a deployed equilibria in the sense if you let the ropes go, it would still stand?
No, so we would have to lock the structure in place, but because it has only a single degree of freedom, we'd only need to lock one or two joints, and it would be sturdy. And in fact, even with friction, some of the designs would stay open. Yeah?
I have a question about your first part about the microstructure design.
Mm-hmm.
So you had this union operation in instead of like the minimum of 2, because you get a sharp corner, you had some
Yeah.
operation, right?
Mm-hmm.
And I guess still in these corners you had the stress concentration.
Yeah.
Is it maybe possible to do some parametric optimization where you only like change the parameters that describe this union operation, so you have very few parameters, and see if that can already alleviate like the stress concentrations?
Yeah, we wanted to look into introducing a few more parameters into to describe the joint geometry, but then it becomes more difficult to formulate the self-supporting constraints to make sure that that it preserves the printability criteria. Yeah, but yeah, that is something that we could look into. I think in our final designs, the stress distributions on the surface were fairly uniform, so I don't think we're that far from the optimum. But I'm sure we could still improve them.
Coming back to this first part, so you have a collection of microstructure.
Mm-hmm.
Are you sure they are really isotropic, all of them?
Yes, yes, up to machine precision.
You have 4,
Yeah.
you have, 4 connecting on each face. They are more or less in a cube, right? Where you start
Right, yeah.
transiting to get isotropic stuff, but then you have 4 points, so is it not? There are many that are almost isotropic, but not really isotropic.
Yeah,
Which ones are isotropic, really?
yeah, so we pick a target elasticity tensor that is perfectly isotropic, and then we're able to fit to it with like a distance of like 10 to the minus 10, 10 to the minus 15.
And during the
So-
optimization, do you put it as a constraint, or you
Yeah. Yeah, our optimization has a constraint on the target, the homogenized Hooke's law, inequality constraint.
Okay, yes, we should move on.
Thank you.
Much.